So our next step, once we've gathered this information, we need to organize it somehow. Now, tomorrow we'll talk a little bit about creating frequency tables and stuff like that. Or over the next week or so, we'll talk about creating frequency tables and stuff like that. For right now, one of the things we want to look at, something I'm hoping most of you are pretty familiar with, and that's graphs. Now, we're not talking about, y equals 3/4 x plus 2 type graphs that we did a few weeks ago. That's not our purpose right now. We're done with those for now, at least until you take your test. What we're looking at is data graphs. For example, one that I'm hoping all of you are familiar with is a bar graph. A bar graph typically is used for one of two things. Well, there's two different types of data we gather. We have categorical data and numerical data. Numerical? Numerical just means the result. When we're gathering data, we're asking a question. And the data itself is classified by what the answer to that question is. If I'm asking you, who are you going to vote for in the next election? Your answer puts you into a category. Candidate A, B, C, whatever. It puts you into a category. Or if I ask you what your favorite color is, answering that question puts you into a category. Red, blue, green, whatever. A numerical piece of data, or a numerical question, your answer would be a number. In fact, how old are you? How tall are you? How much do you weigh? What's your GPA? How much do you earn? Your answer to that question is a number. Bar graphs are typically for categorical data. For example, let's say I do ask, what is your favorite color? Now, we only have 5 students in here right now, so that makes it a little tougher. Heard one pink.
Yellow.
Well, because of the lack of respondents, let's narrow it down. Let's say you can choose red, blue, and green. It's like whichever one's closest to you.
If you do that, you know what, I'm not going to choose.
You're going to refuse to participate. You're going to take your toys and go home?
I would refuse.
Okay.
None of those are my favorite colors, so I'm not doing it.
Or if I asked what of those 3 colors, which one would you prefer?
That's different.
Green's probably closest to yellow. So we have our list of colors, and then we have our frequency over here, or how many people chose that color. And let's just, for the heck of it, say we had 7 people choose red, 9 people choose blue, and 4 choose green. How would we make a bar graph? Well, bar graph can go one of 2 ways. I usually make my bar graphs vertical. In statistics, vertical graphs tend to be more accepted, but it could be horizontal as well. So I'm just going to put red, blue, green. And up the side, I have to have some sort of numbering system. That 1 through 10 is going to be just fine. I don't have to number every one of them. I'm just going to number 5 and 10. And you can figure out in between what each of those marks means, right? And now we need a bar. For red, that bar has to go up to a 7, which is right here. For blue, it has to go up to 9, somewhere in there. And green has to go up to 4. Now, a bar graph, like any graph, has strengths and weaknesses. For a bar graph, its main strength is you can very quickly look at it and tell what color was chosen the most. Blue. What color was chosen the least? Green. Now, in this one, you could probably do a pretty good job of asking how many people chose blue or green or red, because you can look at it and say, hey, it's like 7 chose red, 9 chose blue, and so on, because the numbers are relatively small. But if I had surveyed like 200 people, well, something that might be hard to tell, is that at 39 or 38? What exactly is it at? So a graph, it's good for telling which one's the largest or the smallest, or comparing to. If I asked you which was choosing more, red or green, you could very quickly say red. But it's a graph, especially a bar graph, is not good at getting exact numbers. Now, we also mentioned the possibility of a horizontal bar graph. that would have looked like this. You'd have put red, blue.
Question.
Yeah.
I was kind of confused. You're saying finding a 9 on that one would be easy, but finding a 9 on, say, 49 would be harder. I don't quite
Okay,
understand why
that's a
you
very
would
good
be
question.
harder.
So anyway, it's a horizontal graph, looks something like this. You get the picture. Why would it be more difficult to get an exact number if there was larger numbers? Because let's say that there was, let's say my numbers,
And that's pretty simple because it's a flat line. So if you take a piece of paper and lay it on there, you're going to go right too.
Yeah, but here I'll show you this. So let's say that's our numbers right there. Oh, let's see here. It's not going to get up there, am I? Be careful on my number. Because I have to go up to 89, I'm not going to number every one. I have to go with 5s or 10s or whatever. So now for my bar for red is 89. Now looking at that bar, is that 89? Is it 88? Oops, I got to go up one more. I got to go up one more. Is that 89 or 88 or 90 or where exactly is it? Same for the blue. Go 71. Goes at 70, 71, 72. Getting the exact number is almost impossible there. So the larger the numbers get, the more spread out the scale is going to be. So that's harder to get exact numbers. But that is a very good question. Yeah. So if you want exact numbers, go back to a table of some sort. Other types of graphs. By the way, for numerical data, there's an equivalent to a bar graph called a histogram. If this were a more detailed statistics class, we'd talk about histograms. Like if I were asking what your height was, the height of students, so I can't just say, 5'1", 5'2", 5'3", because there's way too many heights to put them all on the graph. So you might have like 60 to 64 inches, and then 65 to 69 inches, and have it in groups like that. Then your histogram would have bars that went up like this. A histogram is on the homework?
Maybe it's the study plan. I don't.
It might be in there, but it's still.
I was working with that.
I think the textbook still refers to it as a bar graph rather than calling it a histogram. If you wanted to get into technical statistics, it is called a histogram, not a bar graph. But they look the same. One of the two big differences between a bar graph and a histogram: the bar graph has categories instead of numbers, and you'll notice I left space between the bars in a bar graph. In a histogram, I put them tight together. So that's the second difference, is that the bars in a histogram touch each other, they're tight together. The reason for that, there's a psychological and mathematical reason for it. There is no connection between red, blue, and green. I could put them in any order and it would make sense. There's no connection, there's no logical progression from one to the other. But here, first of all, it does make sense that 60 to 64 comes before 65 to 69 because that's the order, numerically that's their order. Second, 65 comes after 64. They are connected together. Therefore, the data graph, the bars should be connected together. That's kind of a vague answer. I can go into a lot more detail, but we just don't need to quite get there. It's partly the psychological response in your brain. You see the bars connected, you think connection, because there is a connection. So they want you to think about that connection. So anyway, talk about a circle graph. A circle graph is also mostly used for categorical data. It can be used pretty much for the same material as a bar graph is. But a circle graph has one added bonus to it. It is best at showing parts of a whole. For example, it might be a monthly budget, breakdown of a budget, or the breakdown of your time at work. So let's say we'll do the time at work. So let's say for your time at work, You have breaks, email, chatting, coworkers, bosses, online, whatever. Actual work.
I never looked at that chatting time on. Is that me with your teacher's position?
Here? Well, I have office hours, so that's all I do. I've worked a lot of engineering jobs where you get up, you go get a cup of coffee or whatever, and you'll stand around for 15 or 20 minutes and talk to others. But it's, networking and stuff like that is kind of what it's considered. But there are a lot of manufacturing. You don't do that, but there are a lot of office jobs where you do spend probably half an hour out of your 8-hour shift.
I've worked a lot of places. 90% of them are sitting around doing nothing, and they get paid more than you get paid when you go to work.
Because they've been there longer. So it's in
their personality.
Oh, yeah.
Just because they can.
Sure. Let's say your breaks amount to 1 hour a day. Your emails, hour and a half. Chatting, let's call it an hour. So your actual work is 4.5 hours out of your 8-hour shift. Actually, that's not uncommon, by the way. Most studies have shown that in an 8-hour shift, you get 4 to 4.5 hours of work out of the employee. I'm not saying everybody. I mean, there are employees that are better, and there are employees that are a lot worse.
Most of them will stand around and do nothing.
Yep. So anyway, this is a perfect set of data for a circle graph. I mean, we could make a bar graph out of this. It would be okay. But what this is it's taking a shift and breaking it down into the parts of that whole shift. So since it is parts of a whole, it is perfect for a circle graph. To make a circle graph, however, we need percentages. We need to figure out what part of the whole it is. And generally it is percents that we use. To figure out the percent, we first need a total. We add that up. Hopefully it comes to 8 hours because that's what I was shooting for. To find the percent then, so 1 out of 8 would be how much out of 100? If you cross multiply and divide, that's 12.5%. 1.5 out of 8 equals how much out of 100? If you cross multiply and divide, that comes out to be 18.75%. Well, 1 is still going to be 12.5%. 4.5 is going to be 56.25%. That's 4.5 over 8 equals blank over 100. You guys okay with calculating the percents? I know I kind of flew through it. Now, back in the day, you would now take those percents and say there's 360 degrees in a circle, so 12.5% of that is 45 degrees. So then we're going to take out a protractor and measure out 45 degrees. We're not going to do that. If you want to graph that exact, there are tons of computer programs out there now that will make a perfect little circle graph for you, and we don't need to do that. For the purposes of this class, all I'm really concerned about is that you can rough it out. For example, on a circle, half a circle would be how much? 50%. A quarter of a circle would be 25%, right? So now back to my actual data here, and I was going to take red lines and put over the top of this. I got 12.5 and 12.5, which add up to 25%. So that's each of those should be half of a quarter like that, right? So this would be breaks. This would be chatting. Now the 56.25 is a little bit more than 50, right? I'll do that. Something like that. That's my actual work. And this is email. There we go. We broke it down.
You cheater.
That's close enough. Like I said, if you want it exact, that's what computers are for now.
Make them different colors.
Yeah, if you want to. You can dress them up, make them pretty. We've already established long ago that I'm not an artist. So. Okay, that's not, you do have options. What I did here was a bare minimum line graph. I could take this other crap out of here so it doesn't confuse it. That right by itself is an adequate line graph. In many cases, they will like actually put in, 1, 1, 1.5, 4.5, like that. They'll fill it in there so you can match it up, but they don't have to.
On the computer, it has percent inside.
Well, on the computer, you can actually, with like in Excel, you can actually check boxes of include the percent, include the data, include the frequency, stuff like that. Include the category name. Now, sometimes they'll color code it rather than putting the category name in there and stuff like that. Yeah. There's all sorts of different options of what information you want to include or leave out and stuff. Okay. The next type of graph is a line graph. A line graph is quite different because what a line graph shows, rather than measuring different possibilities and comparing the frequency of those different possibilities, the line graph looks at one thing and looks at it over time. For example, a line graph might look at tuition cost. Now, I'm going to do a little trick here, and I'm going to discuss this in a second. Since tuition costs have never been below $100 since 2000, I'm going to put that. What does that mean when I put that on there? That means I'm not starting at 0 and numbering my way up. That means I'm taking a break and I'm starting at 100 here. So I have to be careful. I got to be really careful about this. That type of thing can be done on any graph, and I'll show you in a minute why it can be bad. So in 2000, tuition was like $102. So I'll put a dot right there. 2005, it had gone up to about $124. 2010, it was at 141. 2015, it is at 144 or something like that. So it hasn't gone up much. Now, a line graph has some strength. Again, it's showing change over time. Just like the other graphs, where like the pie graph is, again, showing you that part of the whole. The bar graph, it's really easy to find the largest, the smallest, or compare to. A line graph's strength is, I can first of all pick up very quickly where it's increasing or decreasing. Now, of course, this graph is never decreasing, is it? Because the line's always going up. So I can see very quickly that the tuition has never decreased.
Unless in 2016 it goes down.
It could, yeah, in the future. Yeah, we can't say anything about the future.
Lines in the front that you can still bring it back down.
Yeah. It also tells us where it's increasing the fastest or decreasing the fastest. Here is where the graph is the steepest. Since the graph is the steepest, that is where the fastest change is occurring, is where it's the steepest. Make sense? So that is our most rapid change. Since it's increasing there, that's the greatest rate of increase. So that's what a line graph is good at. Now, there are other types of graphs that I'm not going to discuss much. One of them is called a pictograph. I'm just going to assume, first of all, that most of you can handle a pictograph. Ask me what's the best use for a pictograph. I will tell you flat out, in my opinion, there is none. I am a statistics purist. I do a lot of statistics outside of this building. I'm very particular about how statistics are done. Pictographs are bad because pictographs can be very deceiving. I'll show you one example. Let's say that I am comparing my company A to company B. And I want to look at customer approval. And here's company A has 40% customer approval. Company B, which is me, has a 50% customer approval. That's a form of a pictograph. How's it different from a bar graph? Because I threw in those third dimensions. Guess what? This is really all that matters, is how those line up. That's what the data really is. But by adding this width and this depth, I made mine look huge compared to my competitors. The information on there is accurate. It's just mentally it's deceiving. Psychologically, and there are people and there are branches of statistics based on the psychological effects of those things that are used in advertising to psychologically use statistics to use accurate statistics to elicit an inaccurate response. It's called the human response, where you can use an accurate statistic, you can use an honest statistic to dishonestly elicit an incorrect response.
Okay, so if one of your employees came up to you, big PowerPoint presentation, how would they, you could make the company better than how and that guy, yeah, no, one comes to it.
Well, like I said, I've never been in that position where I'm trying to promote a company. So I'm a quality, I use statistics for quality control and stuff like that. So having accurate, honest statistics is huge in those areas. So I've seen way too many spots where statistics have been used to deceive. For example, I mentioned this little break in the graph when we did line graphs. Let's say I'm comparing companies A, B, and C again. And this is in thousands, or let's say millions of dollars a year of production, of sales. Looking at this graph, if I'm company B here, it looks like I have almost double the sales of company C and double to triple the sales of company A, doesn't it? Because of the nature of the graph. But if I look at the numbers, company A is about 122,000. Or 122 million, I should say. Company C is here like 123 to 124 million. And I'm up here like 126 million. I'm just a little bit above them. In fact, if I were to make a full-blown graph without that break in the axis here, it'd probably look something like this. When drawn like that, it doesn't look like there's much difference between us, does it? No, but drawn like this, it makes me look like I'm more than double A, company A.
It doesn't matter who's looking at it, 'cause I didn't see it.
Okay, but I mean, all I'm saying is you have to be careful.
Two numbers over there, and if you just glance at it, you can see there's only 5 between these two numbers.
Yeah,
It's
but a lot of people don't have that attention to detail. They just look at it and say, "Holy crap, that one's huge compared to that." I mean, that's that psychological effect. There is that 10% of the population that does pay attention to those details and catches it. It's the 90% that doesn't pay attention that's going to be fooled by that they're shooting for.
So
Yeah.
that's okay.
I'm saying you are unusual that you notice those details, and that's a good thing.
Psycho and unusual, he's doing good today. I didn't know he knew that was talking to us.
There's a new quiz due tomorrow and a new homework. Now, as we go through the next couple of classes, you guys are going to find out that there are a lot of things in statistics that can be used to deceive. Through Monday. A lot of things in statistics can be used to deceive, and they drive me nuts because Mark Twain once said, there are lies, there are damn lies, and then there are statistics. There's a lot of truth to that. I mean, you can take true statistics and use them to just twist the truth so horribly.